So we have our new type of function, our family of function, the inverse trig functions. But in order for them to be useful, we want to perform calculus on them so that we can solve good problems. So y equals the inverse sine of x. Well, if I was to rearrange that and make it x equals sine y, because I know how to differentiate the sine function. So if I find dx dy instead of dy dx, differentiate sine, we know we get cosine. So to get dy dx, turn both sides upside down. So there it is in terms of y. And I suppose in terms of y, that's a perfectly fine answer. I mean, substitute the y value in instead of the x value. But we would prefer it in terms of x. So how can we get back to x? Well, we know x is equal to the sine of y. We've got the cosine of y. So I'll change cosine of y to be the square root of the cosine squared. Cosine squared I can then change to be 1 minus sine squared. And sine is x, so we end up with 1 over the square root of 1 minus x squared. Okay. Let's do the same thing with inverse cos. And so x is cosine of y. Differentiate cosine, we get minus sine. So now we have minus 1 on sine y. So same sort of situation. Change the sine y to the square root of sine squared. Sine squared is 1 minus cos squared. But this time we get negative 1 on the square root of 1 minus x squared. And I guess that makes sense. If you think of the two graphs, just like the sine graph and the cosine graph are the same graphs that have just been shifted a little bit. Well, it's the same with the inverse cos and inverse sine graph. So yes, at the same x value, we get the same slope. It's just one's the negative of the other. Okay, inverse tan. So let's make x equal to tan y. Differentiate tan, we get sec squared. Turn upside down. So once again, I've got it in terms of y. Let's change it to terms of x. So sec squared we know is 1 plus tan squared. In this case I don't need the square root because I've already got the square there. And tan is x, so we get 1 on 1 plus x squared. So to generalise all those then to any function of x, well, start off with, if it's just a linear function, so x on a, then we end up with 1 on the square root of a squared minus x squared. Inverse cos, we end up with minus 1 on the square root of a squared minus x squared. Be careful with inverse tan, because you actually get a on a squared plus x squared. It's very easy to make a mistake and put 1 there because 1's on the others. So that's why I tend to prefer this one, because it's more consistent. So if you have inverse sine of the function x, you get the derivative over the square root of 1 minus the function squared. Inverse cos, you get minus the derivative over the square root of 1 minus the function squared. And inverse tan, you still get the derivative on top. So you get the derivative on 1 plus function x squared. So I find that personally easier. Mind you, having said that, if it is just a straight linear function, then the top ones are probably easier to apply. So if I have inverse sine of 5x, I actually think here, even though yes, this is a linear function, I actually think the second formula is quicker than the first formula. Let me show you. Oh, there's the answer. Bang. Because think about it, you're going derivative of 5x is 5. Over the square root of 1 minus the function squared. I've got the answer. If I use the x on a, did I do it there? Oh no, I didn't. So let me just describe it to you. If I did the x on a would be 1/5. And so I'd go 1 on the square root of 1 on 25 minus x squared. We don't normally like fractions on fractions, so I've got to tidy the fraction up and a bit of work to get to the answer. So having said those top ones are great for linear functions, I'm not going to clarify that. Linear functions where the constant's on the bottom of the fraction, not on the top of the fraction. It's a very limited case, I guess. I guess the advantage of the second formula is that we can have any type of function, it doesn't have to be linear. So minus the derivative on the square root of 1 minus the function squared. So minus e to the x square root of 1 minus e to the 2x. Okay, here's one where yes, that first formula would be easier because it is on the form x on a. So using the formula I can go, oh well, it's 1 on the square root of 9 minus x squared. Of course if I stuck with the other one, I'd go the derivative 1/3 on the square root of 1 minus the function squared. So it's not a lot of work because the denominators, whilst they look different, are actually the same. Because one's 3, the other's the square root of 9. which is 3. So if I just multiply everything by 3, eventually we get 1 on the square root of 9 minus x squared. But remember, when you're multiplying everything by 3, under the square root sign, you're really multiplying by 9. So you get 9 minus x squared. E to the power of inverse cos x. So it's actually an exponential function I'm differentiating. So exponentials, we said differentiate the power, put that out the front. E, power doesn't change. So it becomes minus 1 on the square root of 1 minus x squared times e to the inverse cos x. I probably put the it makes it a little bit neater. Put the e to the power on the top of the fraction, make it all one thing. Inverse tan of x cubed. Notice we don't write it as -3. Okay, I know with trig we put the powers there. We don't do that with inverse trig. Okay. So bring down the power, 3, lower the power, 2, put the boot in. Differentiate inverse tan, 1 on 1 plus x squared. So we end up with 3 times inverse tan of x all squared over 1 plus x squared. X squared inverse tan x cubed. Product rule. Write down the first, x squared. Diff the second. Okay, the second is an inverse tan function, so it's the derivative, 3x squared, over 1 plus the function squared, x to the power of 6, plus, write down the second, inverse tan of x cubed, diff the first, 2x. I suppose I could factorise the x out, but why bother? It's not that much neater. Here's an HSC question. 2018. That's last year. Yes, you're right. It is the one we talked about the other day. But let's just reinforce what I was talking about there. Function x is inverse sine x plus inverse cos x. Show that the derivative is equal to 0. So differentiate inverse sine, we get 1 on the square root of 1 minus x squared. Differentiate inverse cos, we get minus 1 on the square root of 1 minus x squared. Equals 0. Hence or otherwise, prove that they're equal to. Well, the key to this, and no, you didn't get penalised if you didn't write it down because it was only worth 1 mark. But the fact that they're continuous functions over the domain, there is no break. You can say it's going to be a constant value for the whole of the domain. So I subbed in 0. It's the easiest one, I think. Again, the order that you see, the 0 and the pi on 2 is important, equals pi on 2. And then it said sketch it. And the biggest mistake, of course, would be drawing the complete line, but it's only going between minus 1 and 1 because of the domain of our problem. As opposed to this one. And I think I did mention this the other day. Oh yeah, try this one. Okay, let function x be the inverse tan plus inverse tan of 1 over x. Again, we make it the exact same question. What happens? Show that the derivative is equal to 0. Oh, okay. Well, I'll get 1 on 1 plus x squared plus derivative on 1 plus the function squared. Well, derivative of 1 on x is minus 1 on x squared. 1 plus the function squared, 1 on x squared. So multiply everything in that second fraction by x squared, and yep, sure enough, you get 0. Okay. Now notice I haven't bothered with the second bit about showing it's a constant, because of course it's not in this case. It just simply goes to sketch. But you see, this one isn't continuous. You can't sub in x equals 0. So you have to investigate both sides to see what's happening. So at x equals 1, we get the constant value of pi on 2. At x equals -1, we get the constant value of minus pi on 2. So our graph here, on the right-hand side, and on the left-hand side, we get a graph that looks like that. Okay. So no, it is not true to say that if the derivative is equal to 0, then the function must have been a constant. It's a constant over a particular domain. Alright, so 1D is our differentiating of our inverse trig.